Here we go with number 5. This is 2007 AB and BC, number 5. There's a lot of subtle information as we read this. So there's going to be some things in here that we don't need yet, but we'll get to eventually. So the volume of a spherical hot air balloon expands as the air inside the balloon is heated. Okay. The radius of the balloon in feet is modeled by a twice differentiable function, r. So we can take the first derivative, represented in the table, and we can take the second derivative. So there's no place where the derivative or the second derivative doesn't exist. That's going to come in handy. Where t is measured in minutes, and it's good that we know it's feet and minutes. Keep the units in mind. For 0 to 12, the graph of r is concave down. I wonder why I need that. We'll find out later. The table above gives selected values of the rate of change of r prime of t. They did not give me the radius. They gave me the rate of change of the radius at specific times. Between 0 and 12, the radius of the balloon is 30 feet when t equals 5. That's going to come in handy as well. And they gave us the formula for the volume of a sphere. So let's jump in with part A. Estimate the radius of the balloon when t equals 5.4 using the tangent line approximation at t equals 5. Is your estimate greater or less than the true value? Give a reason for your answer. Well, let's not answer the is it greater or less. Let's actually not even find out what happens at 5.4. Let's just go ahead. The reason we have tangent lines is to make an approximation anyway. So let's go ahead and make this approximation. So 5a, blah, 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 tangent line. Y minus y1 equals m. X minus x1. I'm actually doing the exact same thing I did when I worked this one out myself, and I kind of used the wrong variable. So I'm going to shift gears for just a second. The x is actually t, and I'm going to be a little more specific with what I'm doing here. So t minus t1, and y is r, so r minus r1. There we go. So that's more what I need. That's sloppy, but there. I marked it out. Hope that doesn't bother you. I want to use the tangent line approximation at 5. Now, you're probably like, well, what about 5.4? No. Hold up. I'm going to use the tangent line approximation at 5 to figure out what happens at 5.4. And that's what we do. And let me get off track here for just a second with a random scrap piece of paper. If I have some curve and I have some point and I have a line that's tangent at that point, then because they're super duper close in a little area around that, I can use the tangent line to approximate what happens around that specific point. So right now I'm doing this for 5, and I want to know what happens at 5.4, wherever that is, but it's going to be pretty close. And it's a really good thing to do if I can find a tangent line at a point, but I don't know the actual function. It's really handy. Okay, so let's keep going. I want to know what happens at 5. So I need a coordinate. I need 5. I need to know what else goes with 5, like 30. So here we go. R minus 30 equals, don't know m yet, t minus 5. And I actually do know m. I do know my slope at 5. That's the rate of change at 5, and that would be 2.0. So 2. And if you leave the 0.0 off in your work, not a big deal. It's fine. They did that just so they could be all decimally. So r equals 2t minus 10 plus 30, so plus 20. And we just found the equation of the tangent line. So good for us. But actually, I'll go ahead and tell you, you don't get any points for that because we need to find what happens at 5.4. So let's go a little bit further and let's find r of 5.4. By the way, this one is calculator inactive. So 2 times 5.4 plus 20, and we can do this without a calculator. We don't need a calculator. 2 times 5 is 10. Okay, great. 10. 2 times 0.4 is 0.8, so 10.8 plus 20, so 30.8. There we go. That's it. Now, we still haven't finished answering the question because they said, is your estimate greater than or less than the true value? Give a reason for your answer. So now we got to think about, well, is it greater or less? And your thought might be, well, I don't know the actual value at 5.4. And that's okay. You don't have to. And here's why you don't have to. So much information in this paragraph. But here it is. It's concave down. So let's go back to this graph I drew where I was doodling. And I drew it concave down, not even thinking ahead of what was about to happen, but concave down. And then I drew a tangent line. And so I said, well, this is what happens at 5.4. Well, because it's concave down, then is 5.4 an overestimate or an underestimate of the actual value? It's going to be an overestimate. So let's just go ahead and write that. Is your estimate greater than or less than the true value? My estimate is greater than the true value. And why? Because it is concave down. Now, I just said it. Don't use the word it when you're doing this. They don't know what it is. What's concave down? R prime, R double prime. Well, R is concave down. So R is concave down. And I want to be specific here because maybe it's concave down somewhere else, but it actually needs to be concave down at 5.4. So I'm going to say for every value between 0 and 12, because they said so. They told me that, but they told me that so I could answer this question. All right, let's go to part B. Slide up a little bit. This actually turns into a related rates problem, and it's an easy one, but a tricky one. It's kind of odd. Find the rate of change of the volume of the balloon with respect to time when t equals 5. Indicate units of measure. Okay, so what I like to do in a related rates problem is list everything I know, and then plug it in and go from there. This time I'm not going to make my list, but I am going to say that I'm looking for, well, the VDT, because they did say that. So that's what I'm looking for. That's what I'm wanting. But here's the formula that I have. 4/3 pi r cubed. Lucky me, they gave me that. Although you know that anyway. We'll take the derivative and we get 4 pi r squared times dr dt. And now what I'm going to do is just plug in everything I know. So the rate of change of the volume at a specific radius, when t equals 5. Okay, so here I could write that down if I wanted to. I could. But I need to know a few things in order to really do this. Like, I need to know what R is. Don't put 5 there. The R is the length of time. It's 5 minutes. I need to know what the radius is at 5 minutes. And don't put the 5 here. That's not what the rate of change of the radius is at 5 minutes. But I can find those things because they told me all that stuff. So here goes. I know I'm switching back and forth. Let me go back to here. They said, find the rate of change of volume of the balloon with respect to time when t equals 5. We put the units of measure in a minute. But t equals 5. When t equals 5, we're at 30 feet of radius. So there we go. 30. This is calculator inactive, but don't panic. That's just 900 right there. You've seen 900 before. Let's see. I also need dr dt. I need the rate of change at 5. The rate of change at 5 is given to me in the table. It's 2. Okay, great. Again, calculator inactive, so there we go. 900 times 2, that's 1,800. 1,800 times 4, that's 7,200 pi. Please don't multiply that out. That's just ridiculous. Leave it at 7,200 pi. And then it said indicate units of measure. Well, I have just found the rate of change of the volume with respect to time. Volume is measured, in this case, in cubic feet. Time is measured in minutes. So there we go. Oh, I haven't told you what everything is worth. We'll come back and do that at the very end. All right, part C. Use a right Riemann sum with 5 subintervals indicated by the table to approximate this. Okay, now what in the world is this? And then using the correct units, explain the meaning of that. So let's just go ahead and talk verbally about that before we write it down. So I'm about to approximate it, so I can't really say it equals because it technically doesn't. And so I need to put the little squiggly equal sign. If you put the real equal sign, it's technically not right because this is an approximation. And the reason it's an approximation is because we don't have all the values. We don't have a function. We have a table. And so let's look at what this means though. The integral of a rate gives you a quantity. And we've talked about that. The integral of a rate gives you a quantity. Well, if I want the integral of my rate of change of the radius, then I get the radius. So in a minute, I'm going to get this and I'm going to be like, oh my gosh, it's my radius. We'll put it in a different context, but it is my radius. Okay. So I want to do a right Riemann sum with 5 subintervals. So here's a rectangle, here's a rectangle, here's a rectangle, here's a rectangle, here's a rectangle. And I'm going to go to the right. So here's my first rectangle, and I'm going to use 4.0. Here's my second rectangle, I'm going to use 2.0. So I'm going to point, and then I will write. So first rectangle is 2 wide, 4 high. Second rectangle is 3 wide. Don't put a 5, it's 3. 2 high. 2 times 1.2, 4 times 0.6, 1 times 0.5. Let's write all that down and we'll figure it out without a calculator. It's very doable. 2 times 4.0, 3 times 2.0, 2 times 1.2, 4 times 0.6. And if you're worried that they're going to count off because you didn't put 0.0, you're good. Don't worry about it. That's not something they look for. Final answer needs to be 3 decimal places where necessary, but for now we're good. 1 times 0.5. Okay, and this is equal to, and it is truly equal to, like this is an approximation of this, but this is about to become an exact number right here. Okay, so I know I've gone from almost is to is, but yeah, it's different. 8 plus 6 plus 2.4 plus 2.4, again, plus 0.5. And here we go. That is 14, 16.4, 18.8, 19.3. And I'm not going to use 3 decimal places because if it truncates, meaning like that's it and there are no more other decimals here, then I don't need to put 0, 0 or whatever. You could, but you don't have to. So there we go. We have figured it out, but have we answered the question? Yes and no. Using correct units, explain the meaning of that in terms of the radius of the balloon. So now let's explain it. Let's like verbalize it, but on paper, which means I'll write it instead. 19.3 what? Well, it's my radius, and my radius is measured in feet because, again, the integral of a rate gives me a quantity. My quantity is feet. This was the rate of change of feet, so now this is feet. So, from t equals 0 to t equals 12 minutes, the balloon, hot air balloon, grew. Let me change the wording of that. The balloon's radius increased by 19.3 feet. Okay, now that's not to say the radius is 19.3 feet. Maybe they didn't start at 0, but it grew by that much. All right, now, part D. We have to talk about whether this is an overestimate or an underestimate, and this is where things get tricky. Now, you could look at this and say, oh, well, these numbers are going down, and that's fantastic. Yeah, that's fantastic. But we don't know, we can't really figure out what's in between those gaps. Let's get a little more specific. This is going to come back to in figuring out if this approximation is greater than or less than the actual value. This was an approximation that we just figured out. Now we want to know, is it bigger or less than the actual value? Let's go back to this phrase right here. It's concave down. This is going to get wordy, but here we go. If R is concave down, then R is either increasing at a decreasing rate or decreasing at a decreasing rate. Okay, let's put this in context here. I'm going to go ahead and start writing the actual answer. Since R is concave down, all right, because R is concave down, R prime is, okay, R is doing something at a decreasing rate. Its second derivative is negative. When we talked about concavity, we were talking about the second derivative. We were talking about the derivative of the derivative. Meaning, whatever is happening here, that's down, then R prime is negative, right? Or R prime is decreasing. Let me reword that. R prime is decreasing. So R prime is decreasing. If this would have been concave up, then it would be increasing at an increasing rate or decreasing at an increasing rate. So R prime is decreasing. So, okay, let's go back to this idea. Because these numbers are decreasing, and you could tell that from looking at the table, but this is like, it's consistently concave down because, again, we don't know what happens in between these numbers, right? So this is like consistently concave down, right? So if I want to tell if it's greater than or less than, well, if this thing is going down, and I'm going to draw it before I finish my sentence. If I've got this graph that's going down and I did a right-hand sum, then I've not counted some stuff that I should have counted. So my estimate is less than the actual value. It could stop there, but I'm going to be a little more specific of what I was looking for. There we go. All right, let's talk about what they were looking for in the answer key. Let's go all the way back to part A. Part A. They did not give you credit for finding that or that. They did give you credit for this, and they also wanted you to give the reason. There we go. Part B, you got 2 points for finding that. Oops, I just said that wrong. You got 2 points for finding that, and you only got 1 point for finding the other. So I have to somehow erase with whiteout. Man, I missed. There we go. So 2 points for finding that, 1 point for finding that, the actual value. And they did want the units of measure, so I'm assuming that the units of measure would go along with that point right there. So no units, but you got the number right, you probably wouldn't get any points. Part C, your approximation was worth 1 point. And your rationale, your answer, your explanation, I'm sorry, was another point. And you better have the word feet in there too. Part D, you would have, I just saw something that I needed to point out. Part D was actually just 1 point. So this was just 1 point right here. Now let me back up. The extra point is the units here and the units here. And so if you had like both of them, you got your point. So I was mistaken. Like if you left those off, you missed a point. Or left one of them off, you missed a point.